All right, welcome to section 6.1 on the table method, which is an introduction to the simplex method. So here we're going to learn about standard maximization problems in standard form, select variables, the table method, basic solutions and basic feasible solutions. Then we'll look at basic and non-basic variables and then kind of summarize here. So the table method is going to be our introduction to the simplex method, which is coming later. And these are going to involve maximization problems with constraints with less than or equal to. Okay. And so what we're going to do is we have this definition, and the definition says a linear programming problem is said to be a standard maximization problem in standard form if its mathematical model is of the following form. So we have some maximize profit, usually is what we're looking at, such that equals C1 times X1 plus C2 X2 plus so on until we get to CK XK. And then we're subject to the problem constraints that are of the form AX1 plus AX2 X2 and so on. And they all again have to be less than or equal to. And our B has to be a number that's greater than or equal to 0. And we have our non-negative constraints. So usually it's restricting the X1 and X2 to be greater than or equal to 0, or the X and Y, but it could be multiple depending on how many Ks we actually have. Now, the mathematical model is a standard maximization problem in a standard form, and the coefficients of the objective function can be any real numbers. So an example would be if we want to maximize p equals 50x1 plus 80x2, that's our objective function. And then we're going to be subject to, and sometimes they put subject to, sometimes they put st. And it's going to be x1 plus 2x2 less than or equal to 32, 3x1 plus 4x2 less than or equal to 84. And those are going to be two of our constraints that are just there, problem constraints. In this case, they talked about one of them's a cutting department, and the other is assembly department. And then we also have our non-negative constraints. The x1 and x2 both have to be greater than or equal to 0. So that's kind of how our problems are going to be set up, and that's kind of the standard form. Now, what we're going to happen is we're going to have to add some slack variables. And so what this is doing is we're using these to convert the problem constraint inequalities, such as over here we have the less than or equal to, into a linear system of equations where we have the equality. So we're going from the inequality to the equality, and basically we're converting the E system by adding slack variables. So this one is called the I system, which is the inequality. These are the actual problem constraints. And again, they could be pulled from anywhere. They could be these two constraints here or whatever they are. And then what we do is we're going to add a slack variable. And so the first equation, or the inequality that we turn into an equation, we're going to add S1. So we're going to say plus S1, and then we're going to leave a space and say equals 41. Our second one, we're going to add S2 and then equals our 12. And so those are after our slack variables have been added. In this case, we have slack variable 1 and slack variable 2. Now, the solution to the inequality system is basically just x1, x2. But our solution to this E system, we have x1, x2, s1, and s2. So we actually have four variables we're going to get a solution to compared to only the two with the inequality system. Now, a feasible solution with slack variables only includes non-negative values. That's the key. There has to be non-negative. So if you end up with a negative value in there, we basically throw that away. It's not a feasible solution. And so that's kind of a key thing. So whenever you get you'll see here in a little bit, we'll get a table. And if you get any negative values, we don't even calculate P, because then what we could do is we're going to calculate some P based on what we get for X1, X2, S1, S2. We'll get a P values. And if you have any of them that have a negative constraint here, we don't even look at the p-value. So sometimes, you might have half of them that have negative values. We just throw those away. So those are not feasible. So let's look at an example here. So we're supposed to use slack variables S1 and S2 to convert the I system to an E system. Then we need to find the basic solution for which X2 is equal to 0 and S1, which is equal to 0. All right, so again, this is our I system, and we want to convert to an E system. So if we're going to convert to an E system, we have to add an S1 to the first inequality to make it an equality. So we'll have a 3x1 plus a 2x2 plus S1, and then we have equals 21. Then if we have that, we have x1 plus 5x2. Now we have plus S2, and that equals 20. Okay. And most likely, we're going to have, there's going to be other pieces here. You're going to have x1 and x2 greater than equal to 0. And then here we'll have x1 and x2 greater than equal to 0. So that's kind of key things that are they're kind of there, but the constraints only are those two, and this is then our overall have non-negative constraints. Okay. All right, so that's converted to our E system. So again, let's write the E system here. And so now we know that x2 is equal to 0 and s1 equals 0. So what we can do is we can plug those values in to those two equations and see what we get. So what we'll have is we'll have 3x1 plus x2 is 0, so that's going to go to 0. S1 is 0, so that goes to 0, so that equals 21. So x1 is equal to what? Well, it's equal to 7. Okay. Well, now we know x1, x2, and s1. So guess what? Now we can solve for s2. So now we have 7 plus 5 times x2 is 0, and then plus s2 equals 20. Now we solve for s2, subtract 7, so s2 is equal to 13. So now we've got x2, s1, x1, s2. Okay. And now what we need to do is we need to write our basic solution. Now our basic solution doesn't have any negatives, so that's the key thing. And it's going to be x1, which is 7, comma x2, which is 0, comma s1, which is 0, comma s2, which is 13. And so that is going to be our basic solution to this E system coming from our I system. All right, so let's pause there and we'll come back for more.